So today's lesson is going to be on the relationship between delta G Gibbs free energy and equilibrium. So if delta G equals 0, then we know that the system is at equilibrium and no longer able to do work. Remember, when in equilibrium, the rate of the forward equals the rate of the reverse reaction. So the rate of the forward K1 and the rate of the reverse K minus 1 are equal. Because of this, we are able to see a direct relationship between our equilibrium and our delta G. And that is delta G equals delta G prime plus RT natural log of Q, where delta G is our free energy. And this is dependent on conditions that the experiment is under, such as the concentration of reactants, the concentration of products, okay, these types of things. Delta G prime is free energy, except at standard states, okay, so that's important. R is our gas constant, 8.31 joules per mole Kelvin. Be careful because we know delta G is in kilojoules and our R is in joules, so we're going to have to do some conversions. T is the absolute temperature of the reaction, and that's going to be measured in Kelvin. And Q is our reaction quotient, which we have already learned about in our equilibrium mini unit. So at equilibrium, if Q equals K and delta G equals 0, then we can plug in 0 for delta G, and we can plug in rearrange. And when we rearrange, what we end up with here is delta G prime equals negative RT natural log of K. And our K can either be the pressure or the concentration, Kc or Kp. Okay, so if delta G prime equals 0, we are at equilibrium. If we are less than 0, what that means is our K is greater than 1, therefore products are favored. If our delta G prime is greater than 0, what that means is our K is less than 1 and reactants are favored. So K can either be Kp for pressure, which is our gases, or Kc for concentration, which we use when we talk about solutions. But the larger the value of K, the more negative delta G is going to be because of this relationship between the two. So a larger K means our equilibrium is further to the right, okay? A delta or a greater than 1, the larger the K, products are favored. And a negative delta G means that our reaction is spontaneous in the forward direction. And this makes sense, right? Because delta G is less than 0, so that means delta G is negative. And we know that a negative means that it is spontaneous in the forward direction. All right, so it is going to make products, and it's going to do so naturally without any help from an outside system. If we make more products, products are favored. K is greater than 1. Make sense? All right, so if delta G is greater than 0, then that means delta G is positive, which means we are not making products. Our reactants are favored. All right, these reactants do not want to become products. Therefore, my K is less than 1. So let's look at our relationship here and let's kind of summarize. Delta G is greater than 0 and K is less than 1. Then our reactants in this case will be in the greatest concentration. If delta G is only slightly greater than 1 and K is much less than 1, then our reactants are in very high concentration. On the flip side, if our G is less than 0 and our K is greater than 1, products are high. But if our G is only slightly less than 1 and our K is much greater, our products are in the greatest concentration. All right, and that makes sense if you think back to whether it's thermodynamically favorable. How thermodynamically favorable? Is it switching far to the right? Is it switching far to the left? So instead of memorizing this chart, my suggestion to you is to kind of think through it logically. So let's do an example with some calculations. Given the reaction below, the standard free energy change, delta G prime, is negative 0.97 kilojoules per mole at 298 Kelvin. Let's calculate the equilibrium constant at this temperature. So delta G prime equals negative RT natural log of K. Now remember, R has the units of joules, and delta G is in kilojoules, so we have to do some conversions, all right? You have to have the same units throughout. So we're going to convert our delta G from kilojoules into joules. So when we convert, we know that there is 1,000 joules for every 1 kilojoule, so negative 97.7 kilojoules is negative 970 joules, and that is joules per mole. So we plug that value into our G. Our R is 8.314 joules per Kelvin, and it is a negative R, times the temperature, which is 298 Kelvin, and then we're going to take the natural log of K. So when we solve, we get 0.392 equals the natural log of K, and then to get the natural log of K, to solve for that, we're just going to do e to the exponent of our value we got, 0.392. So when we plug that into our calculator, we get 1.48. So because delta G is negative, it is negative, K has to be greater than 1, favoring products, and our K is greater than 1, favoring products. So this is a good way for you to check your work as well. Did you plug it into your calculator correctly? Is everything looking like it should be? Okay, did you get a value that makes sense? Always stop and think, does this make sense? It does. I need a value greater than 1, favoring products. All right, so let's look at this. Here we have a delta G is 104.13, and our temperature is still 298. So let's calculate the equilibrium constant for this reaction at 298 Kelvin. Again, we're going to convert delta G from kilojoules into joules. Then we're just going to plug in our values. So here's our delta G, negative R, K, and then our natural log of K. So when we solve, we get negative 42 equals the natural log of K. So that is e to the negative 42, which equals 5.58 times 10 to the minus 19. So because delta G is positive, which it was, K has to be less than 1, favoring reactants, and my K value is less than 1, which means that reactants were favored.